Dinkar Sitaram, Technical Architect, HP India. Welcome, sir. And he's going to conduct a workshop, and the topic is going to be building and scaling applications to the cloud. Talking about Dr. Sitaram, he is a Chief Technologist at HP System Technology and Software Division, and he focuses on driving the adoption of cloud and self-filling technologies. He's one of the key individuals responsible for driving file systems and storage strategy, including cloud storage. Please come in, sir.
Thanks very much. So am I audible over there at the back? Great. Fantastic. So I'm going to talk about some techniques for building and scaling applications to the cloud. So much of the material I'm going to talk about is in the book which I've recently written. So this book is a developer-oriented book, and the first part of it is about cloud systems, the APIs for using cloud systems like Amazon, Azure, HP Cloud System, and some open source ones like Eucalyptus Open Nebula. Then the second part of it is a technical one. The first part of it is how do you write programs on those systems you want to get started. The second part of it is how do those systems actually work, how do they scale storage, how do they scale computation. The final part is more future oriented. It's about emerging cloud standards, what are some of the recent trends that are there in cloud, and so on and so forth. This came out in the US, and you have a flyer at $60 US. The Indian edition available on Flipkart is at 400 rupees or so. Without much ado, before I actually start on that, I'll just give a quick overview of cloud models and so on. So if you look at cloud computing, we all know the essential characteristics: rapid elasticity and self-service, on-demand, resource pooling, and all of that. So all of these require, the basic thing that they all require is high scalability and on-demand scalability. So how is that achieved? That's what I'll be talking about. And this scalability has to be done in the context of all the cloud service models. So if you look at the infrastructure, you have the hardware at the bottom, and if you look at the infrastructure as a service model, the people that is like typically like Amazon, the people see virtual machines on which they can load any OS and so on and so forth, virtual storage. So how do you scale this? In the platform as a system, people will typically see middleware, like in the case of Azure, which we'll be talking about. They see the Azure storage and things like that. How do you scale that? And also in software as a service, how do you scale that as well? These are the NIST definitions. So basically, in the infrastructure as a service part, people see virtual systems. In platform as a service, people see middleware, which is like web servers and that kind of thing. And in software as a service, people will see software like Salesforce.com is a typical example of a SaaS provider. You can use their own, you can use their application to write your own CRM, or you can use their APIs to develop your own application. So these are things that we're talking about: scalability, availability, and performance. So this is an overview of the talk. So first I'll talk about scaling storage. So in scaling storage, first I'll talk about the basic techniques. Then there's an interesting cloud company called Netlog, which has put out how they scaled, how they started off, and as the load grew, what are the techniques they use for scaling their storage. I'll talk about that. Scaling storage in existing cloud systems. So if you take systems like Azure, Windows, Azure, and so on, how do you scale it over there? Now with storage, one of the interesting things that happens is as you start scaling it, there is a problem, and that problem is that of consistency. So what are the challenges needed to ensure consistency? And then how do the existing systems like HBase, which is part of Hadoop, and Azure and so on, how do they tackle this consistency problem? After talking about scaling storage, I'll talk about the compute. So again, we look at some of the basics techniques, and then how you scale in HP Cloud System Matrix, Amazon, and Windows Azure. So this is just an overview, and more details are in the book. So scaling storage. So this is again the things we said we'd talk about, and the basic technique that people use in when they want to scale storage is that of partitioning. So I'll talk about that first, and then go on to the rest of the things. So before talking about scaling storage, I'll first give a sort of level set about the types of cloud storage that there is. So there are again 4 kinds of storage. There is the file storage, database, key value stores, and what are called XML databases. So I'll go over each one of these in more example. So file-based storage is sort of like which allows you to store a file in the cloud, and typically then you copy the file into your local system and then use it. So a typical example of that is Amazon S3, which stands for Simple Storage Service. This is built on top of HTTP, and this has 2 fundamental concepts, one of a bucket and the other of an object. So a bucket is sort of like a directory, at a top level directory, and an object consists of files which are stored in that directory. And to access a file, you use something typically like this: HTTP get http:/dinkar.s3.amazon.com blah blah, and then /projectfile.c. Now this projectfile.c is the file name. There are no directories. You can have file names which have slashes in them, which look like directories, but they're not actually directories. And so that gives some sort of the organization of the files, but it's not a hierarchical organization like directories. They're just long names. So if, for example, in Unix you have a current directory which will have some files and other directories. It's not like that here. They are just very long names. And Amazon, over here, this shows, if you go to Amazon EC2, this typically shows how you would create a bucket. So you select a bucket name and a region, and once you do that, you can create files inside that. Now the region is a geographical concept. So for example, you can have a US East region, you have an Asia Pacific region, and that shows in which data center your file is actually stored, and that is partially due to legal requirements, because for example, if you're storing data in Europe, they may have different requirements than storing data in US. And partially is due to performance, because if you expect your application to run a European data center, then it may be good to store the data in Europe. Then also you have in Amazon the database oriented storage, which is Amazon Relational Data Store. This is essentially a MySQL database inside the cloud. And so this looks just like a typical database. So for example, if you want to create a database, there is a statement, Java statement. This shows how to create a database in Java. db.createDB instance async parameters. So that creates a database. And once you have once you have created the database, then you can use your JDBC APIs to load, store data, etc. Those kind of things inside the database. Then you have something which is very similar. It looks like a database, but it's not, and that is a key value pairs. So I'll first give an example of how this works. For example, in the case of Amazon, the key value store is called SimpleDB. So you say insert, so you may have an employees record, and you say insert into employees, and you give the value of the fields, the name and title. These are the fields, name and title, and you want to have values, which is Dinkar and architect. And so in a key value store, you have a records which consists of a key and then a value. But the difference with the database is that there is no schema. And so different records have to have the same key field, but they can have different value fields. So in one case, employees can have some records. In this case, I've shown that there's an employee with the key Dinkar and the title is architect. In another employee record, there could be a different field. So now, what is the reason for doing this. So in the early days of cloud storage, many application developers felt that with databases, they were too restrictive for using cloud storage. So you had to have a strict schema. Whereas, for example, if you have a cloud application, you may develop the application, and after some time you may feel that you want to add additional fields to the record. Now, in a database, that requires that the entire database be updated at the same time. Whereas another possibility is that you can update it incrementally. So you can keep adding fields to some records, and so that way, you can take some time. Then again, as we'll see when we talk about consistency, in the case of databases, you need to have, generally it's recommended that it be normalized, whereas that makes certain things harder, as we'll see. And it's more flexible. So I just gave an example of that because different records can have different fields. So if you feel like updating it, that can be updated on the fly. But the disadvantage, of course, is that there's more work in the application. Like, for example, the application has to do all the traditional error checking and those kind of things that need to be done in a traditional database. Then finally, the other kind of thing is what you might call an XML database, which is a typical example is MongoDB and CouchDB and all of that. And those store JSON arguments. So JSON argument can be thought of as being a C structure or a Java object. It consists of name attribute space. So here is an object with name, Dinkar, attributes, and attributes itself is a object with sex, male, title, architect, and so on. And so MongoDB, for example, using the APIs, it can store these documents in the database. And the difference between this and KeyValue stores is that in KeyValue store there's only one key, and the rest of it is a value. So if you suppose you have the key as employee name, and you have one of the value fields is, say, the employee salary grade. So now in a KeyValue store, if you want to find all the employees with certain salary grades, you have to search the whole database. Whereas in MongoDB, you have the API ensure index, where you give the name of the index, and then you can index on any attributes. So that is how MongoDB works. So the difference, in other words, between a KeyValue store and XML database is that in an XML document database you can search on any field, whereas in the KeyValue store you can search only on the key field. So after that, basically, I'll talk about now how the scaling is done. So basically, the requirement is to scale to millions of users, both in capacity and throughput. And the solutions for that in the storage domain are basically by partitioning and replication. And this is a kind of list of all the techniques that are generally used. So the first technique is functional. The first partitioning technique used is called functional decomposition, where you put different databases on different servers. So here is a typical e-commerce site. This is from the MySQL reference manual, where you have a database. You have the data warehouse. Here you have application servers you're reading from the database. This is a content database, so it has things like the catalog and so on and so forth. And this is the e-commerce part of it, which does the transactions, and the data warehouse, which can be used for data mining and so on. So here, if you look at it, you're putting different databases on different server clusters, and the partitioning is by function. And so here you may get a scaling by about 10. So this is obviously not completely adequate for cloud computing, but it does produce a certain amount of scaling, which is by a factor maybe of around 10, 15 or so on, depending on how you can functionally decompose it. The second category is called master-slave replication. And here the idea is that you have a master which takes care of all the writes, and then you have the slaves on which reads can be distributed. So basically you write to the master writes to all the slaves, and then when you have a read, the read can go to any of these. So this is very good for read intensive workloads, and and in practice, of course, there's a limit to how much you can scale the number of slaves, because the problem is that as you increase the number of slaves, the time taken to write increases, because you have to write to n slaves, and even if you do it in parallel, that still causes the write time to increase. So this is a good suggestion for read intensive workloads. Then one other technology that is very widely used and produces very large scalability is called sharding. And sharding is really the same thing as horizontal partitioning or row partitioning in databases. So the idea in row partitioning is that you take different rows of the table and put them in different databases. So there are a couple of different ones, but so one of them you can partition on a round robin basis, which is generally not a good idea because it loses the associativity. So for example, if it's a transaction database and you put transactions round robin in different databases, and you want to find all the transactions for a customer, they'll probably be in different databases. So round robin is not a good, though it's a simple kind of method. The typically used ones are hash partitioning and range based and directory based. So in hash partitioning, you take some object that's of interest, like for example, if it's a transaction database and you frequently want to find transactions by customer, you can hash on the customer ID, and then after hashing on the customer ID, you select which database you want to go to. Range based is the same thing, except instead of hashing on the customer ID, you do a different, you look at a range of customer ID that goes in database 1, a different range of customer IDs goes into database 2, and so on and so forth. Directory based is in some sense a generalization of range based. So you have nowadays software like Memcache, which can keep track of keep caches consistent. So Memcache is an in-memory database which can keep the data consistent in memory across multiple servers. So what you can do is, for each customer ID, you can pick a particular server and assign it to that. So then when you get a transaction or customer, you just look up inside the Memcache database and find out which customer ID it goes to. So that is available now. That is a technique widely used now in Facebook and places like that, because now with servers you can have huge amounts of memory, and the Memcache software allows you to keep it consistent across quite a large number of servers and so on. So these are the basic partitioning techniques. So now one may think that, okay, this row partitioning is a great thing. I have over here, I don't know if this is very visible over here, but this is an example from our book in code on how to write, do sharding over a database using hashing. So over here you initialize the connections to all the databases, and then after that you load the JDBC driver, and then how you direct the query. Okay. Okay, sorry, I think the slideshow, it hid a certain slide. So what I wanted to talk about was, row partitioning or sharding is a great way to increase the scalability. Are there any disadvantages? I think the slide must have inadvertently gotten dropped off, so I apologize for that. I'll make sure that ends up in the final thing that you get. So the main problem with row partitioning is that since the table is partitioned among multiple databases, so many operations become very difficult. One example of that is, say for example, joins. So you would have to do a distributed join across multiple databases, whereas if you want to do this in a regular database, that's very simple. So in the slide also, and I had an example which showed that suppose you want to do a distributed join. Let's suppose that you have a bulletin board kind of a system where you have users who post a topic, and then there's another, so that is one database saying, for example, if you're a user, you start a discussion on, say, infrastructure as a service cloud and software as a service cloud, just an example. And then you have a messages database where you store all the messages. Now suppose you log in and you want to see what have people posted on the topics that I started. So you posted infrastructure as a service, software as a service, and you want to see what other people have posted about that. So if you do this, if your database is not sharded, you can join these two tables and find all the messages. But if the database is sharded, that is partitioned, then essentially what you have to do is you have to search all the databases to find the messages you need. So how do you avoid that? One way to avoid that is by putting your ID inside the message table. But when you do that, the database becomes denormalized, because now you've got the same field in two different databases. And so that is one common way of doing it, but that is the disadvantage of sharding. Finally, the fourth method of doing it is vertical partitioning, whereby you put different columns into different files. So for example, in an employee database, you can put things like a number of years experience, salary and so on in one file, and personal data like address, phone number and so on in a different file. So then the advantage, if I want to do some analysis of things like salary and so on and so forth, I need to read only this file which has the data that I need. So it's much faster. And again, the disadvantage is for some operations I have more complexity. For example, if I want to insert or delete a record, it may involve updating multiple files, and queries with span partitions are more complex. But if I can partition it nicely so that related things are in one partition, one file, that works very well. So the case study what I talk about is of Netlog. This is a European social networking site, and typically I think something like Facebook and so on and so forth. So they initially started off with three databases: a user database, which contains data about the user and messages they posted and the photos they have and so on and so forth. A friendships database which says which user is a friend with which other user, and a messages database. So they initially started off with one instance of all these databases and started off. And the first time they ran into the bottleneck was the user database became a bottleneck. So then what they tried first was master-slave partitioning of the user database. Now this this worked for some time, but eventually that still was not sufficient because there's a high write-read ratio to the master database, because people were updating their photos and so on and so forth. So the master-slave partitioning was not sufficient. So then the second thing they tried was the vertical partitioning, that is, the user database contained photographs and so on. So split the user database into the photos and some other database. So that worked, and that relieved the bottleneck on the user database. And then after that, the message and friendships database became the bottleneck. So then after that, they tried functional decomposition. And in functional decomposition, what they did is put all these three databases on separate servers. And so that again worked for some time. And then when the transactions became too high, each one of those databases individually became a message database. So then finally, the fourth step, they did master-slave partitioning of the message and friendship databases. Now here the message that relieved the bottleneck on the friendship database, but the message database continued the bottleneck because of the high write ratio, because as you can imagine, people are posting messages all the time. So finally what they did was shard the message database on user ID, and that is the configuration which finally worked for them. And so as you can see, they went through a fairly complex process where they identified which database was the bottleneck and kept on using some technique to improve the scalability. So this is a very interesting thing which is on the web, and it can be read by J. Person, database sharding. So now I'll talk about the different. I'll talk about the different how the current storage systems actually handle these things. So the first is HDFS, which is Hadoop Distributed File System. This is modeled after the Google file system, which was pioneered by Google and so on. So in the Hadoop distributed file system has multiple, sorry for the typo at the end, those are data nodes. These are data nodes. These actually store the data, and there's a name node which knows where the file, which nodes in which data node the file is. So what happens is, suppose I want to open a file called F. So what happens is the client sends the F to the name node, and then file F could be partitioned, because Hadoop files are supposed to be huge. File F can be partitioned across multiple data nodes. So it could be the first 1/3 of the file is on one data node, second 1/3 is on another one, and third 1/3 on another one. So essentially HDFS then is using horizontal partitioning, which is sharding. So then the name node comes back and gives the client what are all the data nodes on which the file is stored, and then the client then can go and access whichever data node is needed. So scalability, the file can be split over a large number of data nodes, and it's high bandwidth because the client is directly interacting with the data nodes, so you can get whatever maximum bandwidth is needed. And for availability, data is replicated 3 times by default. Another interesting case study is HBase. HBase is a KeyValue Store, which is part of Hadoop. And so here in HBase, it uses a combination of vertical partitioning and horizontal partitioning. So what happens is that data is actually stored in these H region servers, and the H regions, and the H region server, which is the master, it keeps track of where the data is. So first, the data is stored in column partitioning. So it has a concept of a field, but the name of the field is not just a field. It's specified as a column family : a field. So the column family gives, so all the fields in the same column family are stored in the same file. So first of all, data is stored in column families, which is vertical partitioning, and then within a column family, it's partitioned by row. And here also it's very similar to the, you have APIs like put, which gives a key and a value, or and so on, or get. And this goes to the H region server, which then figures out which H region the correct value and the things are in, and gets the result. So here's an HBase example of how this works. You do the put. First of all, you create a record which is done by the put API, and then you add to the row and then put it in the table column. So I'll talk a bit briefly about how Windows Azure, for example, does storage scaling. So Windows Azure has all of the types of storage we talked about. They've got blobs, which are sort of like the files, file storage like Amazon S3. They've got tables, which are key value stores, and they also have queues which are used for storing messages. So how they again do this is by partitioning. So for tables, which is the key value store storage, you can specify the field which is used to partition the data. So for example, if you've got again, to take the example of transaction data, if you want to frequently access that by customer, you can specify customer ID as the partition key. You can also specify multiple things as a partition key, like customer ID with combination with transaction ID and so on and so forth. For blobs and queues, the name is the partition key. So it partitions based on the name of the file, in other words. Another example is HP's Vertica platform, which does, so HP's Vertica platform is a relational database which is used for data mining. And the interesting thing is it relies only on column partitioning. It doesn't have any row partitioning whatsoever. And it is used for data mining and analysis. So for example, it is used in Zynga, which is the game site, to analyze in real time the user interactions that are going on and try to make recommendations about the marketing campaigns which may be of interest to the user. So next I'll talk about consistency. So if you take a look at, we're scaling databases with multiple replicas and so on. So one challenge is the consistency. Yes. So in consistency, there's an interesting theorem called the CAP theorem, which was first conjectured by Eric Brewer, who was at that time the CTO for Inktomi. And then it was formally proved 2 years later by two people at MIT. So what the CAP theorem says that if you have a distributed storage system, then you cannot have all these three of these properties. You cannot have consistency, availability, and partition tolerance. That means the network between the two nodes breaking down. So let me illustrate. The Brewer conjectured that you cannot have any distributed storage system which has all three of these properties. And so what in practice it means, if you take a look at cloud storage systems, typically they're distributed over a wide area network, and typically they will partition. So what that means is you have to give up one of these two, and typically people give up consistency. So I'll illustrate that with a simple example. Suppose you have a system such as this. So you have got multiple clients. Here is a network, and here are two servers. Let's say take the case where we have replicated the server. The database is replicated among two servers, and you can also this argument also works for the case where the data is not replicated, but part of the data is on one server and part of the data is on another server, and you have to keep them consistent. The example works for that as well. So suppose the network partitions so that this server then cannot talk to that server. Then what are the choices that we have? So the two choices are, first of all, you can say, okay, I won't do anything. So the two servers will operate independently. If you have that choice that the two servers operate independently, then typically what will happen is that the servers will become inconsistent because they can't talk to each other. They cannot communicate with each other. So if you don't like that, then the other possibility is to bring either both the servers down or bring one of the servers down. If you, in either case, what's going to happen is that the server will not be available. If, for example, if you brought one of the server down and this client can talk only to that server, then the server won't be available. So that's essentially what Brewer's theorem, the CAP theorem says that if you have a cloud scale system which can partition, then you cannot have both consistency and availability. You have to decide which is more important and pick that one. So this also you might think that why doesn't this happen in a traditional enterprise data center? And the reason for that, in a traditional enterprise data center, there's enough redundancy that networks don't partition. So you rarely have the situation where two databases in the same data center can't talk to each other. Whereas in a cloud, this could happen. So partitioning doesn't necessarily mean that the internet connection has to go down. Partitioning can also mean that, let's say that there's a lot of congestion in the network, so that when this server sends a transaction to update that server, it takes a very long time to respond. So if that happens also, what will happen is the transactions will start queuing up over here, and then they start timing out. So effectively it's the same thing as the network partitioning, even though the network is not really partitioned. So a practical example of this, which actually doesn't even need network partitioning, is given in an interesting blog by a gentleman named Alan Cockcroft, who is, I think, a senior technologist at Netflix. So what he said is that, Netflix, as you may all be aware, it does video on demand of the internet. So he says, and it runs on the Amazon cloud. And Amazon has an automatic load balancer, as we'll see later on when we talk about scaling compute. So the scenario he considers is this: I have a set-top box over here, and in the Netflix set-top box, you can talk. You can give an example. You can talk about. You can have a list of favorites. So suppose I want to update my list of favorites. I want to add a new movie to my list of favorites. So what I do is I update it over here and then send it to the load balancer. What the load balancer will do is he'll send it to one of the servers. He's doing load balancing, so he'll send it to one of the servers. Now the next thing I do is then I want to see that this was favorites was correctly updated. So what I'll do is I will request that please read the list of favorites, send the list of favorites back. So now this will go again. This request to read the list of favorites will again go to the set-top box and the load balancer. And if the load balancer sends it to this one, I'll definitely get the right answer. If I send it to this one, that depends. If these two servers are synced, then I'll get the correct list of favorites. If these two servers are not synced, I won't get the correct list of favorites. So, in the cloud case scenario, so again, if you read that blog, he's got some interesting ways of dealing with that. So because of this, the CTO of Amazon, called Werner Vogel, he proposed this thing called relaxed consistency. So he said that in the enterprise data centers, when we do an application, we are used to working with strict consistency. But he was saying that in cloud systems, you can't assume that consistency must be relaxed. And so he said the storage system can guarantee different kinds of relaxed consistency, and that could make things easier. So one kind of thing is weak consistency, where the system doesn't guarantee it will give consistent results. So then the application has to deal with it. The application has to somehow decide, was this, and figure out that the thing is inconsistent and deal with it. Another one which is very useful is called eventual consistency. So eventual consistency means you give a consistency window, and you say that after an update, after a certain amount of time, X, whatever that is, 10 seconds or whatever, the updates are guaranteed to propagate throughout the system. So this is a useful thing, because it means that if I make a change and I wait for some amount of time, then I'm guaranteed that the change will have propagated to all the servers. The third one is read your writes consistency. So that means if I am a client, and this goes directly to the Netflix example, if I do a write and then I do a read, the storage system guarantees that it will always be consistent. So this is something which will help you deal with the Netflix situation. And then there's session consistency. Session consistency is a subset of this, where you say the consistency is guaranteed only within a session. So from the storage system's point of view, this is probably weak consistency, and this are the easiest to do, and these are harder to do. So if you look at Amazon S3, which is a file system, in the US standard region, if you got a file which is replicated, all they guarantee is eventual consistency. That means within a certain amount of time, all the replicas of the file will eventually become consistent. And the different regions, they've got different consistencies. So US, West, Eastern Europe, Asia Pacific, they've got read or writes consistency for new objects and eventual consistency for writes and deletes. So all these concepts are in this interesting paper by Werner Vogel. So there is a standard technique for handling this inconsistency, and this is described. This was originally sketched out in a paper called Base, an Alternative to Acid by Brewer, and details were given in Base and Acid Alternative by a gentleman named Pritchett. So Pritchett is a senior technologist at eBay, and he has written, he's given the details how this works. So suppose so acid, I think we're all familiar from it from databases. It guarantees strict consistency like atomicity, consistency, idempotency. I forget what D is, but whatever that is. He says base, on the other hand, is basically available. So that means it's not guaranteed to be available 100% of the time. Soft state, and that means at any point it's not completely consistent, and it's only guaranteed to be eventually consistent. So how does this work? So suppose I've got a user table which has transactions by user, and I have a transaction table which is just the transactions for billing. So how do we update both tables after a user makes a purchase? So in the traditional database method, I'll say begin a transaction, update the user table, update the transaction table, and end the transaction. So then when the transaction ends, both of them are consistent and I know everything is fine. Here in the cloud, this is a very common technique which is used, and that is, this assumes that we have a message queue which is guaranteed to be persistent. So what I do is I first queue an update to the user table, and then queue an update to the transaction table. So because it's a persistent message queue, I'm guaranteed that eventually those tables will become updated. And this queuing and update to the user table can be implemented using a database. I can have a database which is on the same physical server as the user table, and queuing an update simply means inserting a message into that database. And so that way the message is guaranteed to eventually get delivered here. So I queue an update to user table, queue an update to the transaction table, and then I quit, and that's all I do. So by doing that, I'm guaranteed that eventually both these tables will be updated at some point, but I don't know when. So they'll eventually become consistent. So if I take a look at we talked about HBase and how it does scaling. If you take a look at the HBase replication architecture, so if there are multiple clusters, they use a concept. It's called master slave, but that's different from the usual terminology. So what happens is that each table is owned by one cluster, and within this master cluster, it assumes that there's a very fast network and no partitioning, just like an enterprise data center. So within a cluster, it's guaranteed to be strictly consistent. But across clusters, eventually consistent. So what happens is that if an update is made here, the master cluster will eventually send it here. Or if an update is made here, it will eventually get sent to all the other slave clusters. So now I take a look at how compute is typically scaled in many cloud systems. Just like partitioning is the basic technique that people use in storage systems, proxies are the typical basic technique that's used. I'll talk about how those are used in HP Cloud System, EC2, and Azure. So this shows the basic technique of scaling the compute using reverse proxy. The typical reverse proxy, which is very popular, is Nginx. So if you have many cloud applications, then they go to the proxy, and then the proxy distributes it to multiple servers. So that's typically how the proxy is a load balancer. So an interesting thing about the proxies is that proxies can also be used for dealing with the hybrid cloud. So if you take a look at the different cloud models, there are private clouds and public clouds. The private cloud is a cloud that enterprise may have in its data center, and the public cloud is a cloud like Amazon and so on. You can also have hybrid clouds, a mixture of both. And this is an example of how you can use hybrid cloud, how you can use proxies to create a hybrid cloud. So you have clients over here, you have the enterprise data center, and there's a proxy which distributes the transactions of various servers here. If this becomes too heavily loaded, then from the public, in a public cloud, you can create some more servers and have a proxy over here. So then when the transaction goes to this proxy, it will decide whether to send it here or whether to send it here. And here there's another proxy which is distributed. And all of this is controlled by what's called the virtualization manager. So the typical architecture, which is sort of loosely based on OpenStack, is sort of like this. So you have the cloud user interface. There's the virtual infrastructure manager, which looks at the private cloud and also the public cloud, and virtualizes across these and distributes transactions across these. So this is a typical architecture for using a hybrid cloud to scale compute resources. So if you want to do this for Amazon, for example, Amazon has what is called the two methods. There is the Beanstalk, which can automatically scale Tomcat applications. So for that you don't have to do anything, you just need to declare it. There's a Beanstalk. If you go to the Amazon Web Services Management console, there's a Beanstalk tab where you can declare what your application is, the Java components and so on, and that will automatically then get scaled. For other components, you have to set a load balancer. As you can see over here, when you launch the instance, you can specify, you can create load balancers and so on. Through the command line, what you can do is you can create a auto-scaling group. So that's a group of servers which is defined as hosting an application. You can set a scaling policy, and you can create a load balancer over here. So that will then set the policy and add load balancers and automatically scale up and scale down. A similar thing is available in HP Cloud System Matrix. Just a brief overview of that. So HP Cloud System Matrix has what's called templates, which are very useful and interesting for managing cloud applications. So the administrator can define physical servers, virtual servers that are derived from that, physical storage, virtual storage, and you can also define what are called templates. So templates are examples of applications. So this is a template for a 3-tier application consisting of an app server, a web server, and a database. So this just shows the different servers and the connections between them, and you can auto scale this by a tab which allows you to select the minimum number of servers and the maximum number of servers. And this can also be handled programmatically. So you can describe a web service endpoint, which is a group of servers, and set the number of logical servers and add another logical server to the server group and so on. So in the cloud system, it's possible to manually write your own program which will manage the scaling. So in Windows Azure also there's a typical technique which is used for scaling. So in the interest of time, I'll skip some of these and just get to the basic scaling technique, which is so in the Windows Azure, all programs are divided into what's called a web role, which is essentially a program, which is essentially something that runs on a web server, and a worker role, which can be any program and is typically a backend. So the difference is the web roles are stateless and the worker roles can be stateful. So they can be database and so on. So essentially what happens is that you create this with a number of web roles, and the load balancer, the Azure load balancer, which is built into Azure, that will distribute the transactions over the web roles. And since they are stateless, you should be able to distribute them any way you want. Then these web roles communicate to the worker roles by means of queues. And so the web role gets the transaction, and then it puts the transaction into the message queue. And that's where the actual load balancing happens. Suppose, for example, the web role has a rule whereby it look at the transaction and decide which worker role that goes to. So then the web role can look at the transaction, add an extra field which says which is the worker role it goes to, and put it in the queue, and then that will be picked up by the appropriate worker role. Or so basically the web role decides how to do the load balancing among the worker roles. And the scaling can be done manually or via rules, or again Azure has a management API which can do that, similar to the HP Cloud System API. So I think that's the end of what I had to present. Is there any questions? Any simple questions, I'll answer them. So sorry, I think I had a lot of material which I went through at a very superficial level.
Hello.
Hi.
I'm Srinivas. How licensing part will work in this SQL Server or Oracle, in this cloud system?
Yeah, typically I think they charge per usage. So, it will be in terms, for example, Amazon, I think if you have a small instance server, that is 8 cents per hour. And any part of an hour, you pay 8 cents. So even if you use it 5 minutes an hour, you'll pay 8 cents. And if you want Hadoop as well, which is a big data thing, you pay an additional 1.5 cents an hour. They also have similar things for storage. It's based on how much storage you're using.
So shared databases which we are using right in a single server,
yes,
in a virtualized environment.
Yeah, so it is dependent on how much storage you're using and what software you're using. Essentially that's what it is. I mean, Amazon, for example, if you use Linux, for a Linux server there'll be a certain amount of usage per amount of CPU time. If you're using a Windows server, it will be a certain amount, and so on. So it's based on usage essentially.
Okay.
This is Saurabh here, and whether CSA talks to CSM also?
What do you mean by CSA and CSM?
You have one more product, HP
Oh.
CSA from the open group and the software group. So CSM is, I think, up to the infrastructure layer, as per my knowledge.
Yes.
So, like OpenView and other things, so how it is going to be connected? If somebody is having say, existing data center elements, I'll talk about the HP products. Somebody is having HBSM or OpenView. So how it is going to be beneficial for integrating the software piece to the IaaS piece?
Okay, so I think OpenView doesn't integrate with these except as a monitoring solution. I mean, so HP cloud system has more facilities than the OpenView suite of products and so on. So for the cloud system kind of things, which is like creating new virtual servers or deploying as a software as a service and those kind of things, the use of templates and so on. So you would use that. I think OpenView can still be used for monitoring within a server, treating them as independent server, but cloud system also has its own monitoring which monitors across. In other words, if you take a look at the typical cloud system stack, there will be the hardware, on top of that there will be the virtual servers, then there will be the software and so on. So if you OpenView can monitor one particular thing, but when you want to monitor the whole stack, cloud system has its own things, which is also based on, I think, some components from OpenView as well.
Hello, this is Harish.
Hi. Hello.
In NoSQL database or XML database, how good it is to use this as a statistical data storage? Like, Suppose Facebook or Twitter, you post messages for continuously, and at the end of the day, want to see the statistical or analytical reports.
Yes.
So how good it is use this is used?
Yeah, so people have done that. Like I think Facebook uses HBase. I'm not sure, but if you look at the Apache Hadoop suite of products, they have a very large number of things. HBase has data mining software, there's machine learning software, so there's a lot of software which is built on top of that, specifically for that. Now if you're talking about numerically intensive computing, that probably requires its own HPC software. But there is software available in Hadoop and places like that for crunching big data, and that is what, for example, Facebook and Twitter use.
Okay.
Thanks very much. Thank you so much, Dr. Sitaram, for sharing your deep knowledge and expertise. Now, on behalf of UBM, I'd like to take this opportunity to present Dr. Sitaram with a small token of appreciation. Thanks so much. Thanks.